So it's a pleasure to introduce Sinai Robbins from Temple University, who's going to be talking about integer linear programming using differentiable Dedekind sums from analytic number theory.
So, okay. I would like to thank the organizers. What's that? Okay, can you hear? Is it okay? Okay. So this is kind of low tech, but from now on I should start using my brand new Macintosh, which I'm getting used to. I'll define almost everything we talk about, so you don't have to know what Dedekind sums are. You don't have to know what integer linear programming is. Okay, thanks. Cool. And very basically, the problem is given a triangle in the plane. So you have an image to think about. Given a triangle in the plane, is there an integer point inside? What is the structure of the triangle? The vertices are rational numbers. So given any triangle in the plane whose vertices are rationals, find the integer point inside. So to make the problem even more concrete, let's say somebody gives you a rational triangle in the plane, and they give you the 3 vertices as rational numbers, and they say, in fact, I'm going to give you some more knowledge. I'm going to tell you there's exactly 1 integer point inside. Your job is to now find that point. So it's not just enumerating, but actually finding them. And this comes up in encryption schemes and cryptography. A very, very big question, for example, in encryption, is the points in a parallelepiped. Given a rational parallelepiped in Rn, whose vertices are rational points, find an integer point inside, and quickly. So for example, if n is 100, dimension is 100, you imagine yourself sitting inside the unit cube. You look around and there are 2 to the 100 vertices. So just looking nearby is difficult. So let's formalize the problem. So given any rational polygon, polytope P, we're going to list the points. You want to list the points inside. And we'll focus our attention on 2 dimensions, and just so you can visualize everything and be I'd like to be as concrete as possible with these things. So, okay, so this is called the feasibility question in computer science. So this intersects computer science and linear programming people. Although the field of linear programming, real linear programming, and integer linear programming are sort of 2 different fields. And some people that worked on this are Ravi Kannan, Alexander Barvanok, Jesus de Loera, Bernd Sternfels, other people. And so this is a different method, which we started like a year and a half ago now, and it's growing, but I'm just going to present the very beginnings of this. It seems to grow without bounds, but at some point you have to truncate and publish, but that's what I do. All right, so what are these sums? What are Dedekind sums? Let me give you a brief history. So so you know what the problem is now. Another way to visualize these things, to think about these things, is you know what the GCD algorithm is, how to find the GCD of 2 integers, and you can ask yourself, how do you extend this algorithm to higher dimensions? What is a sort of a natural extension of the GCD algorithm to higher dimensions? What does it mean to find the GCD of 2 integer vectors, for example, in 2 space, or so on? So that's another sort of equivalent formulation of these things. So to start, let the fractional part of x be the fractional part, meaning the x minus the integer part for any real number x. And what people usually do in literature, and what I'll do sort of as a joke, is, okay, here you go. Now do what you like with this, right? This is not not a good way to do things, because it's unmotivating. So let's try to motivate more. This is a Dedekind sum. Obviously, you can't stop me from defining it, but it's not illuminating. So what does it do for you? So let me show you what it did for some people through history and what it can do for you. So anyway, so Dedekind, it's called Dedekind. So they appeared classically through Dedekind first. The year was 1892. Dedekind studied this function, which comes up in combinatorics a lot, it comes up in partition theory. You partition an integer into smaller integers, and 1 over this function enumerates all unrestricted partitions. So this is, if you like, this is a generating function for unrestricted partitions. Without getting into that, though that's a combinatorial motivation, a modular form motivation that comes from number theory is you write this function in terms of tau, which lives in the upper half plane. It's a complex valued function. It lives on some natural Riemann surface. Let's see. Down like that? That's better? The other way. Oh, sorry. Okay. Okay, right. So there's the historical Dedekind eta function. Tau is in the upper complex half plane, so it's a complex analytic function entire in tau, but that's the historical motivation where the Dedekind sums appeared. So history sort of, from my perspective, was the wrong way around. Usually it's the right way, but in other words, the more natural geometric motivation for these Dedekind sums are through the geometry of polytopes, which we've discovered more and more in the last decade. So the classical Dedekind sum that we wrote, even though the definition is clear, on the one hand, it's not motivated on the other, but it has 2 characterizing properties which I'd like to delineate and focus on. So the characterizing properties of the Dedekind sums are that it has modular reduction. You can reduce the A mod B and you still have the same function. So nothing just abstractly of a function of 2 integer variables, such that when you reduce the first mod the second, you have the same function. And think abstractly of that function too, such that when you take f of AB plus f of BA, f is S for Dedekind sum, then you have a simple looking rational function A and B. By the way, these are the 1/4 and the 1/12 are Bernoulli numbers, really. So when you extend to higher dimensions, these are Bernoulli numbers. And so you have a reciprocity law. So if you iterate these 2 laws, these 2 axioms for the function, it's exactly like the GCD algorithm. So in fact, you can compute this function very quickly by just plugging in integers A and B and just iterating, reducing A mod B, flipping, and taking the other side, reduce my. So it's exactly the GCD algorithm. So you can do it in linear time, linear in a bit capacity of B. What do I mean by that? So here's the definition. There are B summands. You can do it instead of B operations in log B operations. So the speed is critical for what we want to do. So that's the Dedekind sum and how you can reduce it by these 2 characterizing properties from exponential order complexity to linear complexity. It's a big difference. Now you want to extend this to higher dimensions. So it turns out these things are used to enumerate integer points in polygons. Now if you want to find them and extend to higher dimensions, you'd like to find appropriate functions that mimic this behavior. And we're finding these functions, but they're more complicated. So rather than writing them down, we're finding an axiomatic approach is actually quite useful. So let me show you the axiomatic approach. And the problem stays the same problem. You have, a polygon or you have a simplex in n dimensions, and you want to find an integer point inside. By the way, just what Dedekind did in 1892, if you'd like to see, he looked at the transformation property of this function just for historical purposes. He looked at the transformation property under SL2Z, the unimodular group, and saw that when you apply the unimodular group, the transformation properties give you a character. It's a 24th root of unity, and inside this character appears the Dedekind sum. So it miraculously appeared inside a character which was a transformation law for this function. But that's, again, for us, we're going to focus on the complexity of this little thing. All right. So as we said, just to recap, using both modular reduction and reciprocity, we can reduce the sum to the GCD algorithm, basically. And here's, just to keep walking a little bit through history, what happened in 1951 was Mordell got into the picture, and he showed that if you go from 2 dimensions to 3 dimensions and you ask for the enumeration, how many integer points are inside this 3-simplex, this tetrahedron sitting in 3-space, the simplest possible kind, where the vertices are the origin, A00, 0B0, 00C, and Mordell showed that the number of integer points inside is given by a sum of 3 Dedekind sums plus some innocuous rational function of ABC. And so there was the first historical combinatorial sort of appearance or number theoretic of the Dedekind sums as objects that help you enumerate these things. But I should put a shameless plug for our book with Matthias Beck back there that's coming out at the end of this year. And so where we put a lot of these things together, a lot of these papers, a lot of these results would last like 2 decades together in one place. Springer. Okay. Anyway, Zagier, so just more history. And then I'll go back and refocus on our problem. Zagier studied higher dimensional Dedekind sums, so yet more appearances throughout, sporadic appearances of these things throughout the literature. He had some manifolds. He was studying singularities of cyclic singularities, he called them. And he got these so-called higher dimensional Dedekind sums. These are cyclotomic sums over roots of unity. So if you fix integers A1 up to AD, these are the AD roots of unity. You sum over them this simple-looking function, and you get the so-called higher dimensional Dedekind sum. When the dimension is 2, when you have just 2 of these, and t equals 0, you retrieve actually the classical Dedekind sums we wrote down earlier. Okay. So that appears in orbifold effects of Zagier. And then in a paper that I wrote with Matthias and with Ricardo, 2002, linear Differentiable power Frobenius, the same functions appear in a so-called coin exchange problem. So this is yet a different direction where the same objects appear. So the coin exchange problem tells you that if you have, I'll describe the coin exchange, if given positive integers A1 to AD, whose GCD is 1, it turns out that you can, if you take all positive integer linear combinations, you can achieve every integer after some point. So for example, if you take integers 5 and 12, all positive integer linear combinations of 5 and 12 eventually achieve every integer. The last integer they do not achieve is called the Frobenius number. And Kevin Woods worked on this here. Maybe other people here worked on, and obviously Matthias Beck and other people. So that Frobenius number is very, very interesting, and it turns out that to get a hold of it, we can also use Dedekind sums. And an analogous problem is to enumerate all integer solutions to this. In the first talk by David Bayer, he put the set of all x1 through xd whose sum is 0. That lattice, that d-1 dimensional lattice sitting in RD is completely analogous to this, where instead of x1 through xd, you imagine any other coefficients, a1 x1 plus a2 x2 and so on plus a d xd equals 0. That lattice controls the behavior of this problem. So yeah, so Dedekind sums, they appear everywhere. Okay, so how? What is this? All right, all right. Okay, so here's another paper. I'm advertising Lenny Fukshansky here. So anyway, so another paper that Lenny and I wrote recently on Frobenius problem. By the way, this is something called Ehrhart theory. Anyway, there's a whole body of work since the 60s that tells you that when you enumerate these things, you get quasi-polynomials. So the number of solutions to this linear Differentiable equation in T is a what's called a quasi-polynomial in T. It's almost polynomial, except the coefficients are periodic functions of T. Again, these coefficients are linear combinations of Dedekind sums. So Dedekind sums appear in all of these problems. And one would like to extend them. Oh, by the way, just to sort of, as a cute sideline, I like to mention this. So this is sometimes called the chicken McNuggets problem, the coin exchange problem of Frobenius. So I don't know who first said this. I don't know. Kevin or Matt, do you know? I don't know the chicken McNuggets origin. Anyway, you walk into McDonald's, you order chicken McNuggets. You don't like the name? Okay. Actually, I'm vegetarian, so I never have to do it, but you walk into McDonald's, you order chicken McNuggets, and they want to sell you boxes of 4 chicken McNuggets and 7, and you want exactly 35. You know, 35 is too easy. You want exactly 36. 36 is too easy. You want exactly 39 chicken McNuggets. And so there's a linear combination of 4 and 7 that gives you 39, provided 39 is above the threshold, the magical Frobenius number. So what's the Frobenius number here? It's 4 minus 1 times 7 minus 1, which is 3 times 6, 18. Everything above 18 should be achievable. Anyway, geometrically, you're trying to find an integer point, xy, on this line. So you're trying to look for integer points on this one-dimensional polytope. So this is what you'd like to extend. The vertices of this polytope are rationals, and extending this to 2 dimensions gives you a rational polygon problem that we described in the beginning. All right, so so just again, to focus again on the problem, it's a problem in combinatorial geometry, but arising in computer science a lot. A lot of the historical appearances of these wacky-looking functions appeared in trying to enumerate integer points. But now when you try to find them, when you're trying to actually find integer point, you want a more general sum than just summing one in some object. You want to sum monomials in an object. So there's Grosvenor basis techniques for doing this, but I like to think of it really is a discrete Fourier transform. When you make a change of variable x sub j equals e to the 2 pi I s sub j, when you make that change of variable, you really see it's the sum of e to the 2 pi I vector s dot vector m, which is exactly the discretized integral of e to the 2 pi s dot m, which is the definition of the Fourier transform of the object. So you're looking at the discretized Fourier object of the polytope, and you can capture it algebraically or you can capture it analytically. Yeah, I find it more convenient, to be honest, to capture it analytically, because then I can use all sorts of methods from analytic number theory. But either way, so it's nice. This stuff kind of enjoys being amenable to many methods. Okay, so let's go back again. I'm going back between one dimension and main dimensions just to ground things. In one dimension, what is this monomial generating function? So now we're going to, what is this generating function? You're not calling it integer point transform, I guess. What is this generating function doing for you? Well, in one dimension, if you give me an interval, what's the analog of the triangle in one dimension? You give me an interval and ask me, is there an integer point inside? Well, yeah, I can tell you, right? You can tell me. I mean, this is not too hard, obviously. But what does it mean in one dimension? In one dimension, it's this generating function, which could be a long function, is actually, we know a formula for it. We know that there's a formula called the finite geometric sum. And so what this discrete Fourier transform does for you in higher dimensions is it extends the idea of a finite geometric sum to higher dimensions. So knowing this, so it's kind of funny. It's like, what's knowing? I mean, yeah, I know the finite geometric sum formula, but do I really know it? I mean, if I really, really knew it, I could extend it. So let's look at what we already know and see if we can still glean some information from it. This finite geometric sum formula can be broken up into two pieces, x to the n minus 1 over x minus 1, and then minus 1 over x minus 1. Each of these pieces has a singularity at x equals 1, yet the singularities magically cancel, right? So this is an interesting phenomena that a polynomial can be written as a rational function with some singularities. This thing extends, in one way, it extends into something called Brion's theorem in higher dimensions. But there's another way here in which it extends as well, which I'll describe to you. So this simple-looking thing in one dimension is what we really want to extend. Okay, so back to the original problem. You have a triangle, and you just want to find a point inside. Quickly. And if we can find this generating function with these monomials, if we can somehow get a handle on that, then we can solve this, because so here's the problem. So if we encode each integer point in this monomial generating function right here, if we encode each integer point like this, and we can compute this very long sum quickly somehow, then we're good. So that's the idea, that's the object, the game. So let's pursue this. So what's the simplest possible example in 2 dimensions? The simplest possible example is, as we said before, a rational triangle, and let's make it even simpler, a right-angled rational triangle. So what could be possibly simpler? A right-angled rational triangle with arbitrary rational vertices. Find an integer point inside. Okay, so let's give things names. Give it a name. Label the vertices, arbitrary vertices. The t here is the dilation parameter, so the t controls, you push this line off slowly to infinity, and the t controls the dilation of everything, all the coordinates. And so now this generating function, the discrete Fourier transform of this object, is really this. And t, you dilate the polytope by t, and you want to find this long thing as in terms of a short description. So again, just to refocus our attention on the problem, we have this discrete Fourier transform, and we want to find a short description. We want to compute that. Once we find a short description, that'll tell us these exponents, which are encoded into our triangle. It'll tell us the exponents in a new way, hopefully. Just like in 1 dimension, our old friend from elementary school, the finite geometric sum, wherever we learned it, that encodes these exponents in 1 dimension. Okay, so it's a basic question. Okay, so here's one theorem. So this 2-dimensional innocent-looking thing, let me put it up again here. This innocent-looking sum for this right-angled triangle in the plane, that innocent-looking sum has a decomposition that looks kind of weird into the sum of 3 rational functions. Yet this decomposition is very meaningful and enables us to compute things in what I conjecture to be the quickest possible way. So I don't think, and this is a conjecture, but I don't think there exists a faster algorithm in 2 dimensions. So this is now, as I know, the fastest known algorithm, but I should say Barbanuk's algorithm in 2 dimensions is just as fast. So there's something called Barbanuk's algorithm, and this is really an alternate algorithm for Barbanuk's algorithm. Okay, so how is this different? Well, it's giving you a decomposition of this discrete Fourier transform, this monomial generating function, in terms of new functions, which are now analogs. These new weird functions are now exact analogs of the Dedekind sum numbers. So we found the analogs of Dedekind sums to higher dimensions in terms of these rational functions of several variables now, which extend the Dedekind sums. When you take a limit, by the way, as x and y approach 1, you retrieve the Dedekind sums. So these are now, instead of, remember, Dedekind sums enumerate. So when you want to enumerate things, you had rational numbers, Dedekind sums. Now when you want to find things, you have rational functions. So these are rational functions. And in order to build them up, we need analogous properties. We need to somehow build them up to find them, to compute them, because this is all about computing. And axiomatically, they're built up as follows. So each of these functions, again, this is the simplest possible extension of the geometric sum in 1 dimension. And yet it just still boggles my mind that it's like this, but this is the simplest possible extension to 2 dimensions. But there are analogous theorems in all dimensions. Every dimension has an analogous theorem. In 3 dimensions, you'd have 3 variables. Yeah? Question? Okay. So these functions have characterizing properties just like our old friends, Dedekind sums, did. And bless you. And these functions are now, this is the, you start out with, this is the initial, this is like the Fibonacci, think of the Fibonacci numbers, you have to initialize, f0 is 0, that's this. And then, so that's the boundary value. Then you have to give the modular reduction property. So if you reduce, so if I reduce T mod P and Q mod P simultaneously, if I reduce this one mod this one, I have to tell you what to do, and this tells you what to do. And then if you have a reciprocity law, if you switch things, you have to tell you what to do. And then putting these things together, it gives you exactly the GCD algorithm again. So it's linear time. So you go from exponential time to linear time. So we call these differentiable Dedekind sums for lack of a better word. We might change it later, but I think at this point, because you can differentiate these functions. These are rational functions which you can differentiate. Oh, and we do differentiate them, so. Okay. Yeah, by the way, the methods I'm pushing under the rug, everything I'm pushing under the rug, just this file. Some methods use some discrete Fourier analysis and some complex analysis and so on. Okay, find an integer point inside P. So here's an example. So let's be, again, going back to, you have a triangle and you want to find a point inside. Let's be precise. So if you have coordinates, let's see, we're going to give some very concrete coordinates for these points. This has rational coordinates, which are these two. And now you have these other rational coordinates. So this point, this is the coordinates of this point, but that determines the coordinates of these two vertices. So if you have these rational coordinates, which are roughly 20 bits each, or between 20 and 30 bits each, you want to see how fast you can do it. And so we put Mathematica. At the moment we encoded everything in Mathematica, which is fine. But eventually we might use something else. Oh yeah, let me repeat. Let me give the it's a good. Good question. Let me put the triangle up again. So these are all arbitrary rational. These are arbitrary rationals. So this whole rational triangle, when you oh, I see. Let's see. No, you're right. In 2 dimensions, you can do that, right? In 2 dimensions, you can do that. But this is just an example. Even in 20 dimensions, it becomes already 2 to the 20 choices or rounding. So. Right. You're absolutely right. Yeah, you're absolutely right. So in 2 dimensions, it's absolutely right. But what you can do in 2 dimensions, you can also play a different game. For arbitrary triangles, there's a decomposition. You can take an arbitrary triangle and fit it inside a little box and decompose things into right triangles. So you can use right triangles to attack arbitrary rational triangles. In higher dimensions, actually, I do not know, I have to be honest, I do not know of a way to do that. I do not know of a way to use right-angled simplices and decompose any arbitrary rational simplex by using that in a nice way. But in any case, it's a different problem. Yeah. By the way, we do not need absolutely rational. We do not need right angles, but the formulas come out more nicely. Okay. So here's an example. So the example for this, you just write down the vertices. Mathematica chugs away. It flips, reduces, flips, reduces, flips, reduces. You get a huge rational triangle, and then you hit return, and it comes back with x times y. So I love this example because your iteration. So this is your generating function, x times y. So it shows that the point 1, 1 was in your rational triangle, and so indeed now we use our vision to check, and yeah, there it was. I could have told you that. So that's kind of silly, but it checks, right? It's a good check. Anyway, so just to recap quickly, you have 2 lines of thought: enumerating things and finding things. Historically, Dedekind sums were used in enumerating things, and these differentiable Dedekind sums can be used with the same reciprocity and modularity properties to find points in rational simplices so far, but we're extending it. So I should stop here. You mean a modular function of some sort?
Well, it wouldn't be a modular function, but something with some sort of twisted SL2 type behavior.
Yeah, I don't know. I looked a little bit. Oh, sorry. So the question was, Dedekind found that the Dedekind eta function, when acted upon by SL2Z, on tau, the action is it sends tau to a tau plus b over c tau plus d. And when you plug that into the function, you have some nice transformation law that involves Dedekind sums. Is there an analogous function, maybe not modular, but some analogous function where the transformation law of that function would yield these new Dedekind sums? And the answer is I don't know. But it would be very interesting, yeah. But there should be one, it seems like, but